Okay, how's everyone feeling?
Totally awesome, sir.
So, the question we're going to be answering today is, what is a transformer? And before we answer that question, let me just remind you of Lenz's law here. If you have a bar magnet and you plunge it into a coil of wire, this coil of wire is connected to a light bulb, but there's no EMF, there's no battery. So at first there's like nothing happening. But when you plunge this bar magnet in, the coils of the wire, these coils of wire right here and here and here and here, they're going to be busting through these flux lines right here and right here. And when those flux lines get busted, that induces a current. So there's going to be a new current in this coil of wire, and that's going to make the light bulb go off. Lenz's law says that new current always opposes the motion of the bar magnet. So if this bar magnet was being plunged in, we know that the new current is going to have its own magnetic field. And that magnetic field is going to oppose the motion of the bar magnet. So that magnetic field would have a north right here, because a north is going to repel this north, and like poles repel. So that's going to make it difficult to plunge that north pole in. And then once we establish that this here is the north, then we know that the field lines come out of the north and they go into the south. So this is the south here. And then we could use that second right-hand rule for coils backwards to figure out the direction of the induced current. So if you put your thumb in the direction of the North Pole, your fingertips tell you the direction of the induced currents. So we know the induced currents are going this way. Now, here's the thing. Instead of plunging a bar magnet in and out of that coil of wire, there's another way we can plunge a magnetic field into and out of this coil of wire over here. We could use another current carrying inductor. So if I take a look down here, I have this one coil over here that has a battery and a switch and a coil of wire. And then right next to it, I have another coil of wire that has a light bulb. So at first, there's like no current in that second one to the right, and nothing's happening. But watch what happens, folks. When I switch the left circuit on, well, then this current is going to come to fruition. So this current is going to start flowing. So as this current starts flowing, up like this, a magnetic field is going to come to life around that coil. So as I put this switch on, there wasn't any current to begin with, but as soon as I put the switch on, the current starts flowing, and then I imagine this magnetic field coming to life. So it's like it's going to grow. And when it comes to life, its magnetic field is going to plunge into this coil over here. So instead of having a bar magnet plunge into the coil on the right, it's going to be a current carrying coil whose magnetic field is going to plunge into the coil on the right. So we could use the second right-hand rule for coils, and we could figure out, over here on this side, what's the direction of the magnetic field? Well, fingers go with the currents, thumb goes pointing towards the north. So this here would be a north, and this here would be a south. So I know that these field lines here are going to be coming out like this, and going around like that, and coming back in like this. So it's kind of like plunging a south pole into the coil on the right. By turning the current on in the left coil, when that current starts flowing, and this magnetic field comes to life, well, field lines are going to be busted, and it's like plunging a south pole into the coil on the right. So if you're plunging a south pole into the coil on the right, what pole is going to be formed right here? A south pole. It's going to be a south pole. And this is going to be a north pole. And then I could use the second right-hand rule for coils, and my thumb points to the north, and my fingers wrap around, and I get a little current here. And this light bulb is temporarily going to light up. But here's the thing, folks. It only lights up for an instant. Because once the current goes full speed on the left coil and the magnetic field around it is full blown, then no more flux lines are going to be busted. It's kind of like back up here. Once you put that bar magnet into the coil, if you just plunge it in and then you leave it in there, no more current in that coil. You have to be busting flux lines. So similarly down here, when you turn that current on right here and the magnetic field comes to life, it's only when that field is plunging into the coil on the right that a current gets induced over there. But once the magnetic field due to the coil on the left is full blown, no more magnetic field lines are going to be busted, and then this current here stops. No more light bulb. Now, interesting enough, guess what's going to have, guess what I'm going to show you next, like how I can get that light bulb to light up again. Turning it off. Because when I turn the switch off, see this current going through the coil? It's going to come to a stop. And if it comes to a stop, then guess what's going to happen to this magnetic field here? It's going to drop out. It's going to decrease. So it's going to drop out. So it's kind of like I'm pulling a south pole away. And if I'm pulling a south pole away, guess what pole is going to be formed right here as the current is coming to a stop, and this south pole right here is decreasing away, pulling away. Yeah, there'll be a north here. And if that's a north, then the current is going to flow this way. And the light bulb lights up. But again, does it last very long? No, just temporarily. Just as the field on the left is disappearing, as it's collapsing, the flux lines are being busted once again as it pulls away, and you temporarily get that current on the left. All right, check this out, folks. Here I have a power supply, and the power supply is hooked up to this coil right here. But there's no contact, there's no touching or anything with this coil over here, yes? This coil over here is hooked up to a galvanometer. So at the front board thing, I showed you like a light bulb. This is kind of be like the light bulb, but instead of a light bulb, it's just a little galvanometer with a needle deflection. Now I'm going to turn this current on. When I turn the current on, it's going to start flowing in here, and then the magnetic field is going to come to life. So it's being plunged into this one, like plunging a bar magnet. So guess what temporarily gets induced in this coil? A current, and we should see the needle deflect. But once this current on the left is maximum speed all the way up, then the magnetic field is full blown, and it's like a stationary bar magnet, no more flux being busted, so then the current stops. So let's take a look. Hopefully this works. All right, ready, set, go. Very small, did you see it? It's very small. But now the current is still on, but it stopped. But watch again, if I shut it off, little baby one, yes? Now, we can improve that by putting an iron core in between those two. If I put a bar magnet in between, that should strengthen it. Let's see. Ready, set, go. And then when I shut it off, yeah. Now, you might be saying, geez Louise, why go through all this trouble? Why use one coil to induce a current in a second coil? Why not just hook the power supply up directly, yes? That's a great question. So let's come back up here. Well, the reason we do this is because if you have a different number of loops, you can change the voltage. And this whole thing is called a transformer. Now, of course, this only works when the current is changing. So instead of using direct current and putting the switch on and then switch off and then switch on and switch off, you could use alternating current. So look over here, folks. I have alternating current source. So the current's going to go one way, stop, and then it's going to go the other way and stop. And then it's going to go this way and stop, and then it's going to go the other way and stop, yes? And then the magnetic field is going to come to life one way, and then it's going to stop, and it's going to come to life the other way and stop. And this is going to be happening over and over and over again. So the light over here ends up staying on continuously because the the current on the left, its magnetic field is coming to life, going away, coming to life the other way, going away, coming to life this way, going away, coming to life this way. Now, why go through all this trouble? Because you see the number of loop-de-loops over here? They're called turns. Over here, I have 2 loop-de-loops, 2 turns. Over here, how many loop-de-loops do I have? 4 turns. The coil on the left is called the primary, and the coil on the right is called the secondary. And this whole device is called a transformer. And if the number of loops goes from 2 to 4, the voltage gets doubled. So the voltage right here, if this is a 120 voltage source, well, then guess what the voltage to this light bulb is going to be? 240, because it's stepped up in the number of loops. And this is called a step-up transformer. Now, when you plug in your laptop, I think, uses 12 volts. But the wall outlet is 120 volts. So you see this device right here? It's a step-down transformer. The number of loops decreases. And here's another setup. Instead of having like a long iron soft bar like this, you could just take the iron bar and make it into a donut shape. This here is a step-down transformer because the number of loops in the primary is 4 turns, and the number of loops in the secondary is 2 turns. So if this here is a 120 volt source, guess what the voltage across this light bulb is going to be? 60 volts. It got stepped down. As soon as this current starts flowing, then a magnetic field forms in the coil. But then the current stops, and the magnetic field stops, and then the current starts flowing the other way. And the magnetic field gets formed the other way. So transformers are used to step up and step down the voltage. All right, to be continued tomorrow.